Hello and welcome to Mr. Linford's math course. In this video, we're going to be introducing a topic we previously covered, that of linear equations. But this time, rather than dealing with linear equations in the single variable, we're going to deal with two variables. In particular, we're going to start off by focusing on the components of a graph, a two-dimensional graph, and then we're going to get into talking about the definition of a linear equation, how to represent that on a 2D graph, and then some special case situations we might want to look into. Now first we should remind ourselves about the components of a graph. And in this case we're talking about a two-dimensional graph, an XY plane graph. So when we are going to work on a graph, we are going to set up the coordinate plane, as it's called. We have two axes. We have the x-axis and the y-axis. It's two-dimensional because we have two variables. We have the x variable and the y variable, so we have the two axes to represent them. These are axes. Here's an axis, and here's an axis. Additionally, we can describe the graph in quadrants. Let me label this in a different color. I'm going to label each quarter of the graph as a quadrant. Quadrant 1, this portion is quadrant 2, this is quadrant 3, and this is quadrant 4. It moves in this counterclockwise motion. Now, we label these quadrants because the quantities in each one are different values, in particular different sign values. You'll notice that when you're over on this side, the x-axis goes towards infinity, and when you're on this side, the x-axis goes towards negative infinity. When you're on the top portion of the graph here, the y-axis is going towards infinity, and then down here the y-axis is going towards negative infinity. I like to think of the coordinate plane here, this 2D graph, the xy plane as it's also called, as being two intersecting number lines. We have a number line for x, how we traditionally see it, everything going from negative to positive as we move left to right. But we also have another number line, this time for the y-axis, and we've rotated it. We actually have it moved vertical. So this time we have it going from negative to positive, from down to up. So here's our standard graph. We call it the rectangular coordinate system because you can think of this kind of like battleship almost, where points are plotted on this graph in a rectangular grid system. So we do graphing in a rectangular grid system. We say move so much over left and right and so much up and down. So maybe we would say move 3 units to the left and move 3 units up. And that's where your point is. So we have this rectangular grid system. All we talk about for placement of points is how far left and right and how far up and down to go. So that's why it's called a rectangular grid system. If you look on graph paper, you have a bunch of square boxes, hence the name rectangular coordinate system. But this is the general setup. Another thing I want to point out is the origin. The origin is the coordinate point 0, 0, and that's right there in the center, okay? And I should also point out that these coordinate points right here are represented as x and y. A coordinate point, like I said, it matters how far over left and right you are and how far up and down your point is. So, obviously, when we write a coordinate point, the first quantity tells us how far left or right to go. The second quantity is for the y variable. It tells us how far up and down we went. So that tells us our positioning. This coordinate is the origin. I'll call it origin. And it basically says this is the starting value. This is where you have not moved anywhere on the x-axis or anywhere on the y-axis. You stayed right in the center. Okay. Here is our breakdown of the general graph, our general way of working on a graph. I want to point out that this graph It has a number of names to it. We can call it the XY plane. We call it a plane, not like an airplane, but we call it a plane like a plane of space, right? It's where you're going to do your graphing on. So it's called the XY plane. It's called the rectangular coordinate system. And that's just for the general way of doing this graphing. We have the XY plane that we graph on, the rectangular coordinate system. It's got a bunch of other names to it, but the main title we'll use in reference to this is the Cartesian plane. That is the main title we're going to use to refer to this, the Cartesian plane. The reason we call it the Cartesian plane is it's named after the mathematician and philosopher René Descartes, and it represents this XY plane. So we're going to use these terms here interchangeably in this class. Now that we've reviewed graphing and some of the key features to a graph in the Cartesian plane, I want us to actually go ahead and focus on defining a linear equation, and this time defining it in two variables. If you remember, the single variable linear equation was defined as ax plus b equaling, well, I guess you could say 0 here. Or you might say, I think we also sometimes would define it as, besides 0, you could define it as c, right? But basically, these are all real numbers, and this is your variable. And we said don't let it be 0, okay? So this is what a general linear equation in a single variable looked like. Now let's talk about it in two variables. Let a, b, and c be real numbers, such that a and b are not both 0. A linear equation in two variables is an equation that can be written in the form, and I'm going to say that that form is ax plus by is equal to c. Let's pick apart this definition a little bit, and let's try to identify what it's saying and come up with some examples of what it means to be a linear equation. So first up, a, b, and c are all real numbers, okay? You have to understand that a, b, and c are just numbers. Remember, real numbers are numbers on the number line. Okay? So a, b, and c are just numbers that are on the number line. X and y are your variables. So go ahead and start picking some numbers from the number line. Let's come up with some examples. Here, example. Let's do, 7x plus 3y is equal to 5. There's a linear equation. It's in the form here. The a is 7, the b is 3, and the c is 5. Those are all real numbers, so we're good. Let's do another example. Maybe 1/2 x plus 5/7 y is equal to 5.3 repeating, let's say. Well, I have a number times x, a number times y, and a number, equaling a number. A is 1/2, b is 5/7, and c is 5.3 repeating. Those are all real numbers. They're on the number line, right? Remember, real numbers, basically any number you can think of at this point. There's a very technical definition to real numbers, okay? There's an actual very technical definition, and in fact, that was a huge challenge in mathematics for centuries. It really wasn't until, let's say, the late 1800s, early 1900s, that we started to get real technical definitions for what it means to be a real number. If some of you are interested in that, there's some axiomatic approaches to how we define the real numbers. I like what's the method that's called Dedekind's cuts. Dedekind's, I think I'm spelling this right, cuts. It's an interesting technique of how to define real numbers, but it's very complicated. That's the thing. Our other number systems are fairly easy to work with, but real numbers are quite complicated to describe. So for right now, I'm saying it's any number on the number line because I just want you to think of any number you picture, it's a real number, okay? Even imagine something like pi. Pi x plus the square root of 2 times y is equal to square root 3 over 2. I don't know, I'm just making stuff up here. So pi is a real number. That's on the number line. So is the square root of 2, and so is the square root of 3 over 2. So they're all real numbers, and it's in the form that we want. What about if I said, okay, let's take something like, we'll stick with an easy example, 4x, 3y, and 5. But what if I put a subtraction here? Is that allowed? 4x minus 3y equals 5. A lot of us might at first be saying, well, no, that's not allowed because this is an addition problem, right? The form requires addition, and this is subtraction. But hopefully you're saying to yourself, wait a minute. Subtraction is addition. It's a form of addition. It's where you add the negative. So really, instead of 4x minus 3, we have 4x plus negative 3. Is negative 3 a part of the real numbers? Remember, this symbol right here, it's like a C with a little check mark in the middle. That means is a part of, or is an element of. So are we saying that negative 3 is a part of the real numbers? Well, yes, it's on the number line. Negative numbers count as real numbers, so it's allowed. So we're not exclusive to positive numbers. You could have negative numbers. You could put a subtraction sign in a linear equation if you wanted to. So I'm going to do that right here. Let's put negative. And in fact, let's make it negative 9x minus 5/12 y is equal to 7, whatever. I'm just making stuff up. This is a linear equation too. It's allowed. Now what I want us to do is pay attention to this little caveat part we have here, that A and B are not both 0. That's the one little requirement we have on writing a linear equation. All of these examples are linear equations, but there's this little condition. We can pick anything we want for A, B, and C, but we're told you can't have A and B both be 0. So could you have 0x plus 0y is equal to 5, let's say? Is this a linear equation in two variables? No, it is not, because it does not meet this condition. It says you cannot have both A and B be 0. Well, A and B are both 0 in this equation, so this would not be a linear equation. And it's fairly obvious why. What's 0 times anything? It's just 0. So 0 times x is 0, and 0 times y is 0. Does 0 plus 0 equal 5? No, it doesn't. So that's one of the reasons we're saying you can't have A and B be 0, because you end up with a contradiction. Also, sometimes students will say, well, wait a minute, Linford, here's an easy fix. 0x plus 0y equals 0. That's true, because all of this will just become a 0, and 0 equals 0, so there you go. My response to these students is that, okay, you've created an identity. Remember, identities have infinitely many solutions. You can plug whatever numbers you want for x and y, right? They don't have to meet any special relationship or be chosen in any careful way. Literally, every coordinate point you think of, and every ordered pair, pick any number you want for x and y, it will work. That's what's called a trivial case, right? That doesn't do anything interesting for us. That just says you could literally pick any number you want. There's no special relationship. There's nothing interesting about that. So even this, we're going to say these examples don't do. What about this situation? And I'm kind of running out of room here. Let's try this example. Let's say 0x plus 5y is equal to 15. Is this allowed as a linear equation? A lot of times students might jump and say, no, this isn't allowed. Look, a here is 0. Careful. If you read what the definition says, it says that a and b cannot both be 0. One of them can be 0. That's allowed. However, you can't have both of them be 0. In this case, if we went to solve for this, we would actually have a solution. Y is equal to 3. So we could find a solution for this and a special relationship between x and y. So we are allowed to have one of these be 0. So a here is 0. You could have 5x plus 0y is equal to 17, whatever. This is allowed, right? Because only one of them is 0, not both. Sometimes people will say to me, wait a minute, Linford, what about C? What if we had something like 5x plus 0y is equal to 0? We now have B is 0 and C is 0. Is that a problem? And I always say, read the definition here. Does it say C cannot be 0? Do you see anything in here that says C cannot be 0? Does it specify anything about C? No, it doesn't. So this example right here is, again, another linear equation. It's allowed because the only requirement for us is that you can't have both A and B be 0. Everything else, don't really care about, okay? As long as it meets that requirement, we're good. Now, we've talked about this idea of having a connection between x and y, meaning we have some type of relationship between these two variables, these two quantities. If we're talking about equations, we most likely want to talk about their solutions as well. Solutions to a linear equation in two variables are ordered pairs. They're ordered pairs, x and y. The reason they're ordered pairs is because to be a solution, you have to find something that works for x and y. So a solution to a linear equation in two variables is an ordered pair x and y that makes the equation, I abbreviate that EQ, so it's an ordered pair x and y that makes the equation true. To be a solution to a linear equation, you have to be an answer for x and an answer for y that when you plug these numbers in, it makes the equation true. If it made the equation false, like if one side was in fact not equal to another side, then you know that those values don't make a solution. So, for example, let me clear a little space here. Let's take one of these examples we just worked on. Let's see if we can find a solution for one of these linear equations. Maybe let's take a look at 7x plus 3y is equal to 5. We want to come up with an example of what a solution would be for this. So let's find an x and y that will make this equation true. So, gosh, if I'm thinking to myself here, let's say 7 times something plus 3 times something needs to equal 5. I'm going to say let's have x be 2 and let's have y be -3. Here's what happens. 7 times 2 is 14. 3 and -3 is -9. And the difference between 14 and -9 is, in fact, 5. Or I should say the difference between 14 and 9, that is 5. So it works. So for this equation, 2 and -3 is a solution. You'll notice I wrote it as an ordered pair. I wrote the x value and then the y value. what value you should plug in for x and what you should plug in for y to make this equation true, okay? A coordinate point like, let's take 7 times 1 plus 3 times 2. Does that equal 5? 7 plus 6, that doesn't equal 5. So we would say that 1 and 2 is not a solution. We would say 1, 2 isn't a solution because it doesn't work. It doesn't make the equation true. That's what it means to be a solution, something that makes the equation true. Let's talk about now how to take a linear equation in what's called symbolic form, right, where it's written down with number and variable. And let's talk about putting it into a more visual form, a graphical form. First, we need to really define what does it mean to have a graph. And I always tend to ask students this. I always say, what is a graph? What is it? What is it made of? And students say, well, it's, axes and points. And then I say, well, explain to me, what is the graph of an equation? And students will always say, well, it's a picture of the equation. It's a visual representation. And I say the question again, okay, but what is a visual representation of? And that's where we tend to get stuck. What is a graph? What does it represent? What does a graph show us? If you had to make a graph of a linear equation, what are you showing by drawing the picture that you're drawing? Well, really, a graph is a representation of the solutions to an equation. So the definition for a graph is really the visual representation of the solutions to a linear, let me rewrite that, to a linear equation. That's the thing here. When we graph, we're drawing points basically, right? When you make a graph, you're coloring in dots, little points on the graph, right? You plot a point here, you plot a point here. Those points that you're highlighting, that you're drawing, right? Those points that you're dotting, singling out, you're plotting those points because they're solutions to the equation. That's a really cool thing to understand. A graph is telling you, here are all of the solutions to this equation. And what's really cool about that? First off, let's talk about what the graph looks like. For a linear equation, okay, when you have a linear equation in two variables, you are going to have a graph that looks like a straight line. It is a straight 2D line, okay? That's a really fascinating concept, that in this way of graphing on this Cartesian plane, it just so happens that all the solutions to our linear equation happen to fall perfectly on a straight line. That, to me, is an absolutely fascinating concept. All the points here fall on a perfectly straight line. Additionally, besides just having a straight line, how many points are there on the line? Think about that. How many points make up a line? Infinitely many. When you draw a line, you're representing infinitely many points. We could always just keep zooming in and zooming in and zooming in. So, what does this tell us about solutions to a linear equation? Well, it should tell us that there are infinitely many solutions. To a linear equation, you can always find more and more solutions. It'll always work, okay? You can see that from our previous example here by me just picking other values, right? Maybe I just keep increasing x and decreasing y and keep having a difference of 5 every time. So I can, keep this pattern going. really infinitely many times. I can do it with as large of numbers as I want or as small of numbers as I want, okay? Solutions to equations don't just have to be whole numbers. X and Y are real numbers, okay? They're not just whole numbers. You can have solutions that are decimals or fractions. You can have positive and negative solution values. You can even have solutions that are like pi, right? Things that go on forever and ever and ever. So, this is the idea of what a graph represents. Let's talk about how to actually go about coming up with a graph for a linear equation. When it comes to actually determining what the graph of a linear equation is, the question really is, well, what are the solutions to the equation? How do we go about and find what the solutions are? Because once we know the solutions, then we can plot them very easily. So, how do you go about and find solutions to an equation? Well, in the previous example, I kind of thought of, well, there's a pretty obvious solution in my mind. So when I did this example right here, I could pretty quickly see that 2 and negative 3 would work. Because I was just thinking of small numbers off the top of my head that might go in and work this out. But let's say, how would we find other solutions to this? So the equation is 7x plus 3y equals 5. So how can we go about and finding other solutions that might work? Well, there's infinitely many solutions. We know that off the top of our head. If this is a linear equation, it's going to have infinitely many things working for x and y. Part of what you should understand is if there's infinitely many and it's a straight line, picture the graph of this. If you imagine we have a graph with an x-axis and a y-axis, and we drew a line on here. What if we drew the line this way? Or what if we drew it like, let's say like this? Any of these lines that we drew, imagine they go on forever and ever in all different directions. They go off forever and ever to the left, to the right, up and down. Now take a look at all these x values. Notice that all of these x values, no matter any x you pick, there's always a value on one of the graphs, isn't there? For any x value you pick, you'll always get a y value out. We're going to get to what this means in a couple units later. We're going to connect it to a topic called domain. But for right now, we can really picture to ourselves that since we're going to have a straight line, and it might be tilted in any which way, right? It might be going up, down, might be really steep, really slanted, or really flat. We can just imagine that it's going to keep going out forever and ever and ever. And any x value will intersect the graph. Anytime we pick an x value, there will be a y value, right? And vice versa. We're going to use that idea to help us find different values. Since any x value will give us a y value, let's plug something in for x. Let's just plug something in. Let's say I'm going to plug in the number 4. Let's do that. I'm going to plug 4 in for x. So we have 7 times 4 plus 3y equals 5. What we're going to do is solve for y. We're going to say, okay, if x is 4, what does y have to be to make this equation true? So this would be 28 plus 3y is equal to 5. If I subtracted 28 from both sides, we would end up with 3y is equal to, let's see, 5 minus 28 is going to be negative 23. Y is equal to, if we divide both sides by 3, negative 23 divided by 3. We can just leave it like that. The decimal's like negative 7.6 repeating, but we'll just leave it as an improper fraction. That's fine. So we have gone and said if x is 4, y is going to have to be this negative 23 over 3. There is our coordinate point. There's a lot of ideas coming together here and reasoning out why we're able to do this. But the short idea is you can pick any number for x. It will be a solution. Any number you want for x will be a solution to the linear equation. So plug something in for x and see what y would have to be. And the reverse is true as well. Any value for y will be a solution, right? So you can plug in any number you want for y and see what x has to be. So let's go ahead and write down a procedure for what we want to do to find solutions. If you want to find solutions to a linear equation, you should first select a value for one of the variables, okay? I'll abbreviate that VAR. Select a value for one of the variables. Plug it in and solve for the other. So you'll plug the variable into, you'll plug the number into one of the variables and solve it for the other. And there you go. You have a solution. So there's one solution for you. I'm going to say, I'm going to say first, write the solution as an ordered pair. We should really get in the habit of writing coordinate points or solutions to linear equations as ordered pairs. Okay, we know what that means. We know that the first part's x and the second part's y, so we should get in that habit of doing that. So select a value for one of the variables, plug it in and solve for the other. Write what you get for your answer, and then repeat. Go ahead and repeat this process by picking a different number for one of the variables and solving for the other. You pick a different number for one of the variables, and you're going to get a new coordinate point. How many points do you need to determine a line? Well, you only need 2. So we can say you need to only repeat this once. As long as you can come up with 2 points, you're able to draw your graph. So this is the process that we'll use for when it comes to actually figuring out what the graph of a linear equation in 2 variables is. So let's practice with this example of x minus y is equal to 3. You can go ahead and plug different values in for x. Let's make a little table here. Here's x, here's y. Let's plug some stuff in. Let's plug in -2, -1, 0, 1, and 2. Okay? And let's see what we get. If I plugged in -2 minus y is equal to 3, let's see, I could add 2 to both sides to get -y is equal to 5. So y is -5. Y equals -5. Let's try plugging in -1 minus y equals 3. If I add 1 to both sides, I would get -y. Oh, my stylus isn't working today. We get -y is equal to 4. Y is -4. Y equals -4. And you could continue on and see what your different solutions would be. Like, for example, 0. You could say 0 minus y is equal to 3. So obviously y is going to be -3. You can keep going on. You probably see a little pattern for what the numbers are doing. But we can go ahead and say, here are some solutions. -2 and -5. -1 and -4. And 0 and -3. So we have more than we need. Let's go ahead and maybe plot this. Now, I am not the best at drawing graphs. I much rather prefer working on graph paper or on the computer for this, but I think you get the main idea. Let's go ahead and do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. Okay, the first part is -2 and -5. That means go over -2 and then go down 1, 2, 3, 4, 5. So somewhere down there. Let's say maybe, oh gosh, my stylus won't go all the way down there, but somewhere around here. Now let's take a look at -1, -4. Go over 1 and go down 1, 2, 3, 4. So maybe right about here. And then the last one is going to be 0, -3. And maybe something like this. So we went down 3 units. So we have several points that we can draw a line through. Once we have that line, we can say, all right, we can say that every point on that line is in fact a solution forever and ever. So now we have a visual way of showing all the solutions to a linear equation. Let's talk about intercepts, special points on the graph. If you are trying to come up with the graph of a linear equation, you can go ahead and find 2 points that are solutions to the equation. 2 of the easiest points to find are the intercepts of the equation, the x-intercept and the y-intercept. Now, intercepts are where one of the quantities is set to 0. So for the x-intercept, this is the x value when y is equal to 0. And the y-intercept is the y value when x is equal to 0. That's the idea here. The intercepts occur on the axes. So graphically, this is where the line crosses the x-axis. And the y-intercept is where the line crosses the y-axis. So we have an example numerically of what's going on when one of the variables is set to 0. And we also have a graphical way of showing what's going on here, okay? Let's take a look at our previous example of x minus y is equal to 3, and let's see if we can find the intercept values for this equation. So to find the intercept, the x-intercept, that's when y is 0. So x minus 0 is 3. Okay, x is equal to 3. There is one of the solutions, and it is the x-intercept. To find the y-intercept, make x 0. 0 minus y is equal to 3. So we could say that 0 for x, -3 for the y-intercept, and we should be set. Right now, let's go ahead and take a look at some special case situations we might produce when working with linear equations. In particular, let's talk about what happens when you have a linear equation whose graph is purely vertical and purely horizontal. Now, in all these cases that we've been reviewing, we keep talking about linear equations that could be slanted in all different ways. Right? We imagine that a line could go like this, or like this, or like this, or be really steep like that. But do we ever picture a linear equation being purely vertical. Let me try to draw that a little neater here. A purely vertical line, straight up and down. And close enough. And then, do we ever picture one purely horizontal? Perfectly left and right. Now, these situations are produced when we have very special forms to the equation. So when you have, for example, let's take a look at the horizontal example. If you have a horizontal line, you would have had an equation y equals k, where k is a part of the real numbers, okay? You would have had something like, here's an example, y is equal to 1. Okay, this is a linear equation in two variables. And you must be saying, Linford, there's no way. Two variables, there's only one there. How could this be a linear equation in two variables? Well, really, what I'm implying here is that this is a linear equation in two variables, right? I'm saying, and I'm kind of telling you this because I'm intending it to represent this graph. There is the variable x in here. This still is in the form of a linear equation in two variables. It still meets our definition. Remember, the definition said ax plus by is equal to c. Well, in this case, we have y being equal to 1. B here is 1, but a is 0. Remember, you were allowed to have this situation. This fit our definition. The definition said be in this form, but a and b cannot both be 0. One of them could be 0. Here's the situation where that occurs. Here's when a is 0. It has canceled out the x variable, so all we have left is y. This will produce a horizontal graph for us, because what this is saying is start finding solutions to this. Go ahead, start finding solutions to 0x plus 1y is equal to 1. You'll find that, well, y is equal to 1, that's just a single value, right? Y, if I have to find a value for y, it has to be 1. However, x could be anything. X could be anything because it always cancels out. So I'm going to put in something like 2. Try it. 0 times 2 plus 1 times 1, that's equal to 1. So 2 and 1 works. Let's try a different number. Try something like 7 and try 1. 0 times 7 plus 1 times 1 is equal to 1. That works because this just cancels out. So 7 and 1 are solutions. Try something like negative pi, right? That's a real number. So negative pi times 0 plus 1 times, and we'll have y be 1. Yeah, these just cancel out and you're left with 1 again. So really, it doesn't matter what you plug in for x. You can plug anything in for x, and it will always cancel out. You'll still be just left with 1. So in this case, for solutions to this, you basically can have anything for x, but y is always the value 1, okay? If you picture this on a graph and plot these points, they're all on a horizontal line. What we're saying is x can be anything, but don't go up and down in y. Stay at the same y value all the time. Stay at the same kind of height in the graph all the time. Now, you could also have the situation where the graph is vertical. That's the reverse. That's when x is equal to a number. Let me call it, let's say h, okay? And h, again, this is just some real number. So h here is anything like 1, 2, 3, 4, a half, negative 3/4, 0.7 repeating, pi, square root 2, whatever, okay? When we're saying these are real numbers, we mean any number on the number line, not just specific whole numbers or whatever. So, how is this one different? Well, in this case, we would have an example like, let me think of something like x is equal to, let's say 2, okay? Now, when x is equal to 2, this implies that a here is 1 and b is 0, and that's equal to 2. So that's why you can now plug anything in for y and it will cancel out, okay? This is still a linear equation in two variables. It's just one of the coefficients, the a or the b, one of them was 0. In this case, it was the b. In the previous case, it was the a. This is still allowed. In this case, you have x is equal to 2. If you made a table of values for this, what could you plug in for x and what could you plug in for y? Well, this says x always has to be 2. But you can plug basically anything you want in for y. It will just always cancel out. So we can plug in negative 1, 1, 2, 15, 27, negative pi, negative square root 2 divided by 100, whatever, okay? In any case, we have the same thing for x every time here. Graphically, that's going to produce a horizontal line because all the x values are the same. Y will change, but x will always stay the same. That means we're not moving left or right any value. We're always the same distance over from the y-axis. We're always the same number of units over. Just like before, when the y was constant, we were the same number of units up from the x-axis. Here, we're the same number of units over from the y-axis. So these are the special case situations you might have, okay? They do pop up a bit in class, so we want to make sure we're comfortable with the equations. X is equal to a number, and y is equal to a number. We want to make sure we can picture what is happening in these different situations. And if you're unsure, go ahead and do an example problem. Plug some numbers in, right? Come up with a little example and plug some ordered pairs in to see what the solutions might be. If you have any questions on the video or any of the content, please let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know what you thought of the video, any questions or comments you have, and until next time, take care.